So, statistics and reproducibility. That's the topic for today. And we have been doing a lot of image processing lately. And in the end, we want to take all these images and create some useful numbers out of them. First, we have a little bit literature to take a look at. I think you recognize most of them by now. Some little new things is about hypothesis testing and grammar of graphics. A couple of books, and that can be useful when you start going deeper into the material of today. Then there are also some videos and podcasts. Some is more of the entertaining kind, like this one, making fun of scientific studies, how stupid you can actually make your conclusions based on statistics. And then there is a lot more material down here. This data set is actually the one we are going to use during the lecture. So, as I said, we have been doing a lot of image processing. We have done enhancement. We are trying to understanding the histograms, doing automatic methods to segment and process the images. And then from the segmentations, we have gone into shape analysis and also looking into more complex shapes using skeletons and distance transforms. So we have done a lot of work in order to get from the large images to smaller amounts of interpreted data in some higher level of abstraction. In the beginning, it was only pixels or voxels. Now we actually have put the items you see in the image, put some labels on them, and started making numbers also out of these labels. So, quantitative big imaging, what is it? So, it's not only that it's big or even large. It's meaning being ready for handling big data. And big data is a global concept in data science, that you have not only the data, but also the whole framework of methods around data analysis. You have the hardware to be able to crunch all the data. And that's pretty much a whole framework you have to think about. And it's also how you create these data, or why it becomes big, is that for one thing, you have volumes, you have velocities, you may have varieties. So you need to build up your data set to really cover the field that you want to investigate. In order to handle that, you need to have a framework that is scalable, possibly fast if you can, but also easy to customize, because sometimes you may come to the conclusion, yeah, well, maybe I should look at it the other way around. And from that, you need to modify a little bit and make it possible to do this other point of view analysis. So what we need to do is, one thing is doing the analysis in very disciplined manner. So you should have recipes where you do fixed steps, and it should be easy to regenerate the results of each step. Of course, no magic. As soon as you start doing hand waving and tuning every image, then it's not good. Another important thing is also that you document what you actually are doing. So putting some comments in your scripts or in your notebooks, write up what you're doing. That's also very important, because when you come back to the data 1 week, 1 month, a year later, you don't know what you did. That's will take you a long time to go through and see, in particular, if you use not so explainable, well-explained names in your analysis. So if you only use variables X, Y, and Z, it's probably difficult to understand what you did, particularly if you wait a long time after. Then it's also very important to have the possibility to automate everything. It should be, for you at least, as easy to analyze 100 samples as if you would only have one. So you have, say, a basic work that you need to do in order to get the analysis done. But after that, your extra work should be only that you do a little wrapper around, and then you say, run it 100 times. Here is the data. So that is one thing. And then when we come to the flexibility, it should be easy to actually modify these scripts that you have done in a way that you can handle different types of data in the images. So maybe you have done something. Of course, it's probably not so good to have it's so general that you can analyze cells and monkeys with the same script, but different types of cells. So if it's animal cells or if it's plant cells, they have in some sense similar characteristics. So to do a scientific study is actually to try to get a single number or a plot or something that can make sense from all this data. So you're doing a huge reduction. You had gigabytes, terabytes of data in the end. You want to plot with 10 points. That's an extreme reduction. So you need to have a structure for handling that. The other thing is to know how you should compare different groups. So if you have, usually in a scientific experiment, you have a control group and you have something where you had modified something. And you want to compare if there is a change or how great this change is. Also, how do we compare different processing steps? What is the impact of using different filters, using minimum volume, resolutions, etc. And in this lecture today, we're also going to talk a bit about how to evaluate your parameter selection, how to select the parameters in a way that they are as global as possible. And with that, we also come to the validation. We have to check, is it really true what we are doing? Validation is something we have talked about before. And finally, also how we can visualize data, how to work with different visualization techniques, or actually plotting techniques is it today. Some weeks ago, we talked also about volume rendering and meshing. But today we are going actually to look at the statistical data and how to plot that. So the recipe that we are working with, the steps is usually we have step 1, get rid of the noise and find the cells. That was what I was talking about in lecture 2 till 4. Then analyzing shapes. That was lecture 5. And then separating the cells that were joined somehow was the watershed segmentation in lecture 7. And then after that, we went into also looking into different metrics and characterizing the distributions, which was lecture 7. And so now we have got our data. So now we need to do some kind of analysis out of that. And well, that one I essentially already said, so that was an extra slide in that case. So coming into the scientific part, you have typically 2 terms that are used. One is correlation and the other one is causation. When you look at correlation, you look for a statistical relationship between two groups. It's easy to show. There are simple equations to compute it, just a lot of summing. Causation is something more complicated because it shows effect if you introduce something and what is the effect of that. So if you have started, for example, taking a pharmaceutical treatment, then you have a group which is given some drug, and you want to see what the effect is. Sometimes that's possible, but it's not easy to show that there is an effect between, and at least not if you don't control anything. And proving causation is even more difficult. Sometimes with physical models, you can have some idea, but really proving it is not that easy. In order to check these two, correlation and causation, you can divide your experiment into two broad classes. One is the observational. Then you are only leaning back, looking at what's happening, collecting data, you're making a sample somewhere. The other one is that you have controlled experiments where you really control the parameters you want to investigate. So usually the observational, we have a large data set, typical big data thing that we have a very large data set we want to explore. The population is random, typically. So if you have something, maybe it was collected with some intent, but when you pick your data, you should do some kind of random sampling anyway. It's not clearly that it's hypothesis driven, but it could be. But from this kind of data, it's very unlikely that you can see any causation effect. So for example, we examined 100 people. The one with the blue eyes were on average 10 centimeters taller, like me, blue eyes, almost 190. So that fits in that sense. You could also have 100 cake samples, and you can see a 0.9 correlation between cooking time and the bubble size. So that is something you can just observe. You didn't do anything in particular yet. So these are the observational type of experiments. If you do a controlled experiment, then actually it is the category that most, I would say, most imaging experiments falls into. So you define different samples with different characteristics. Maybe you have some external environmental influence on the sample, and then you look at what's happening if you change parameters in the setup. So we could, for example, have 50 mice with a specific gene on and the same gene off. And you can see that foot size increased by 10% with this gene on and off. Another thing we can look at is if we increase the pore size, the temperature, the pore size in some metal increase by 10%. So that's also, you had a parameter that you tweaked and you see directly an effect in the sample you're examining. That was a little bit too early. So in principle, in the initial phase of your experiment or in your project, you may do rather observational experiments because you want to get a feeling of what is it you actually have to work with. Once you have seen some trends in the observed data, then you can start specifying into control experiments. I want to look into this specific character that changed in the sample and why it happened. And with that, you can start looking at the environment that caused that. And then you can start doing more control experiments and playing with specific parameters where you saw some correlation between sample behavior and the environment. To look into statistics, it's very difficult to take a real scientific experiment because it's usually very specific to some problem. It's noisy and it's not so easy to bring into the lecture. So right now we're going for a very simple model just to show the example of probability. And we have a coin, which we are flipping, that we bought in a shop. Let's call it a magic coin. And the question is how many times you need to flip the coin to prove that it's not a fair coin. So let's try some ideas. If I flip it 10 times and another person also flips it 10 times, would that be the same as doing 20 flips? Or if I flip it 10 times and multiply it by 10, is that the same as 100 flips? You could also put another question. If I buy 10 coins and want to know which ones are fair, what should I do then? So this looks ugly. So better. So each coin represents some stochastic variable x, and each flip represents an observation. So that's an xi. The flipping is actually an operation we perform on the coin. So the coin flip f is is actually an observation from the stochastic variable x. Typically, in a fair coin, we expect the probability of heads and tails to be a half. So 50% heads and 50% tails. So if we have an unbiased flipper, that means we can essentially just multiply the probability of each flip and get the total probability of some event. The expected value then is actually this multiplication down here. So you have a chain multiplication, and that should actually, if you do many flips, it should be the same as the expectation value of the stochastic variable itself. So in the beginning, it might be a little bit biased because statistics, you never know what comes. But in the long run, if you go to infinity, you should land on this half if it's a fair coin. So looking at the connection between model and reality, if we do the coin flipping, each flip that we do gives us a piece of information that tells us something about the coin. Is it fair or not fair? But also about the flipper, the person who flips the coin. And that's actually an important thing. That it's not only the item we study, but also how we modify the item. And as each flip has some kind of random information, we need a lot more flips to provide information about random variations of flipper and coin, because they cancel out. If there is a little bit deviation in one during one segment, there is a different variation in the other segment, and that levels out into the average. However, if there are systematic variations, they accumulate. So if the coin is somehow tampered with, so it only shows heads, you will see that in the trend of the average value. Same if the flipper somehow has some good trick that he always flips up heads, that you will also see. But from this experiment, you can probably not tell if it's a coin or the flipper or it's unfair. For that, you need probably a second experiment. So if we look at real experiments, we have the first that each measurement tells us about our samples, of course, but also about our instrument. And finally, also about the way we analyze the data. All three sum up. And again, we can say that the random stochastic variations in sample instrument analysis, they will cancel out. But normally the analysis have very little, or actually, hopefully, no stochastic variation at all. Yeah, that could be that you are on the numeric boundaries that could give you some shakiness. Or if you use actually some kind of random initialization, then there could be some stochastic variation. But usually the analysis has very little stochastic variation. Systematic variations, again, of course, they accumulate. So if there is something that shows a trend in anything, then it will accumulate. So for example, if you in the analysis set a threshold which is a little bit too high, a little bit too low, that will give an impact on the whole outcome, and that will actually accumulate into the result. If we now look at a little more complicated model, then we can look at this iris data set, which is, what was it, 34, I think, 1934. This data set was measured. It's a number of measurements from 3 different species of irises. And then we can see, and also, of course, a large collection of these flowers. So it's a good data set to play with and check out. If we load it, we can see the information we have. It's actually a standard data set that you can load. Then you can see that we have sepal length, sepal width, petal length, and petal width. And you see the name of the species here. This is just a little collection. So I did sample 5. So it's a random selection of items. And this is what we are going to work with. Now, the pair plot we have seen already in other contexts. For example, when I looked at the sand grains, here we can see that we have the different anatomical sizes here. And the colors we can see are the different species of these irises. And we can clearly see that the setosa is actually separating itself from the other ones, and the other ones, they are kind of clustered, but also more or less clustered actually. And in this case, it's pretty well separated. So if you look at the sepal length to ratio to the petal length, you can see a good separation, but the length to width is more similar. So we can get some information out of this. And now we want to take a deeper look into this data. And we want to compare different groups or different values and see how well you can separate them. And for that, we start looking at the sepal width. And for those of you who are not so into flowers, like me actually, I had to look up what actually sepals and petals are. And sepals are the green leaves that cover the flower bud, and petals are the colorful, beautiful flower leaves, which we usually call the flower. And they have different width and length depending on the species. And here we can see that the sepal width is about the same. So that is something we call, so we have the average value is around more or less the same value. Also, the variance of these is also almost the same. With that, we call it a low group similarity. When we look at the petals, that's something completely different, because here we have a very good separation in the average value, even though the variance is more or less the same. This one is even more compact. So we can see that this one is very well separated and probably also much easier to cluster. And a quantitative statement, so now we just said it had low or high separability. We also can put numbers on, and for that we have this intraclass correlation coefficient, which is the ratio between the standard deviation of the averages and the average of the standard deviations. So this means that if we have ICC equal 1, we have essentially a very good separation between the classes and almost no variance within each class. If it's 0, then it's bad. That would mean we have all values on the same average and very large standard deviation. So let's see what that gives us for the two cases I showed before. Here we can see the interclass correlation coefficient for these two, for the sepal width and the petal length. And we can see that the standard deviation of the variance is about the same as the standard deviation of the averages, and that gives us a group similarity of 50%. So that means it's very bundled together. We can't really separate them. In the other case, we have the average standard deviation is the standard deviation of averages is very large, while within each cluster, the standard deviation is relatively low. And that gives us a high group similarity, almost towards 100%. So that's a really good value in that case. So now we want to compare different groups, and we can list a lot of assumptions, and from those assumptions, we can establish a null hypothesis. That one is usually that there is no difference between the groups. And then we calculate a lot of probabilities and see if the null hypothesis is true or not. For that, we need knowledge about the probability distribution, and this modeling can also be very difficult to get right, actually. That's where the statistics people are coming in. And sometimes you have too little data, and that also makes it hard to get the real probability distribution. So let's come back to the coin again. So we have some assumptions that we have flipped coins correctly and independently. Also that the coin is invariant and always gives the same expected value. So that should be 0.5 probability for both, or the expectation value is 0.5. So that will be our null hypothesis, that the coin is unbiased when this value is fulfilled. Now we can compute the likelihood that a given number, a given observation is true or false. And for that, we use the p-value, and the p-value is the probability that we should reject this null hypothesis. And if you look at the Gaussian distribution curve, which is the one that is very frequently used, most cases you have actually a Gaussian distribution of your observations. And then you make an observation and you compute what is the probability, and that the probability is the area under this in this green area here. And on the top, it's very likely. On the tails, it's very unlikely. So what is good enough now? We could set it to be, to be something. And typically, we need some help. We never know exactly which distribution we have. We can make a good assumption that it is Gaussian distribution, but we never know for sure. We may not have sufficient data to really fulfill this criterion to do a true Gaussian comparison. So for that, we now have the student T distribution, which is used as an approximation for the Gaussian distribution when you have few counts. And that distribution is kind of modulated by the number of cases you test. In the end, you will get out a probability that you should reject or accept your null hypothesis. And usually what you assume is that you have unbiased observations and that the underlying distribution is a normal distribution. So let's test a lot of coins then. Typically, if we have a probability which is less than 0.05, which is 5%, that should be good enough to reject or accept the hypothesis. So would that mean that if we have 5 heads, we are good? I don't know yet. Let's see. Let's first toss the coin and see which probabilities we have. If we toss a single coin, then we have 50% probability of head and tail. But if we would have 4 heads out of a single coin, 4 flips and get 4 heads, then the probability for that is 6.2%. If we would toss 5 times and get 5 heads in a row, then we would have probability of 3.1, and that would be below this p-value of 0.05. And we would say, if we can toss the coin 5 times in a row and also get 5 heads, then we must say, sorry, this coin is surely loaded. We have to take another one to do a fair gaming. So that is one way of checking. Then if we do another way, we can also try a little bit with many people. So now we change also the flipper. So let's n friends make 5 tosses. One friend does this experiment, 5 heads out of 5 tosses, get the 3.1. But if you have 10 friends, all of a sudden the probability to get 5 heads is 27%. Or even if we go up to 80, then it's a probability that you get 5 heads within these 5 tosses is 92%. Doesn't make sense, really. Let's take a look at it. So what actually happens is that this investigation was not based on the right question. So with the 80 friends, you ask for 5 heads out of these 80 friends. And that's not the same as doing 5 heads in a row for one person. So what we said is we want exactly 5 observations and that all of them are heads. And that says that the likelihood for being a fair coin is 5%. So if we add more observations or more sub-experiments, then we also have to scale our result probability with the number of repeated experiments. So let's look at that. We do now a little bit larger experiments, not the coins anymore, but it's some kind of, actually, this is just randomized. But we have different variables that we investigate and want to check if they are fulfilling our hypothesis or not. And you can see here you have group 1 and group 2, and we have some different measurements. And let's see. Here we can see that for variable 3, it doesn't fulfill our criteria. It's even 1% only, but the other ones, some of the other ones, they are okay. If we do a larger table, so in this case, we create 150 rows and 20 columns or 20 variables. And we can see that some of them, they are, well, below the 5% and most of them are okay. So we know now that some variables we have to reject and some others we don't. This can be taken up even larger. So now in this experiment, we try out, see how many variables in the study in this, in the x-axis, and how many significant variables we found. If you have one example, most of them are actually not a significant outlier. But if you increase the number of experiments, you will have more and more, and you can see also that it spreads out. So you have some kind of linear trend here with the number of repeated experiments. And that's not really good because it should be the same process that we're looking at. You can also look at it a little bit differently using a box plot where you can see how the data is spread between quantiles. Here are the quantiles, and then you have the, I think this median value in the middle here. And you can see a little bit about how the measurements are distributed. But anyway, you can still see clearly there is a trend going up here. So one simple way of testing this is to just divide by the number of tests and see what happens. So here you have our significant values from the previous experiment. They go up straight line here. But if you divide by the number of tests, then you can see, okay, we have a pretty nice straight line around here. So this makes it possible to better do this analysis or conclusions from the statistics. But is this correction enough to get the right values? Now let's try out with something else. We have, again, some table with random variables. In one group, we have same standard deviation. It's normal distributed, but the offset or the position is shifted by 1 standard deviation. So it could look something like this. If we only have a single variable, then it looks fine. We have most of it around here. But if you start doing corrections with 18, 35, or even up to 87 different variables, you can see that this tail here is moving more and more towards higher values. So meaning that this scaling doesn't really work. This peak here is just that I clipped and put everything else, but otherwise this tail here, this would actually go out as a long tail towards 1.0. So we will shift out everything, and that's not really the purpose of it. So we need to use maybe better ways of correcting for if we do multiple tests. Also, the likelihood to find a different variable changes. So now in this one, I just counted how many are detected, and with a single variable, it's very easy to find it. It's almost 1. But then it's towards 100 tests, 100 variables, then you are at a very low likelihood to, no, wait, this is % likelihood. Okay, but anyway, it's a factor 2 about between 1 variable and 100 variables. So we need to do maybe going into some other methods and doing this kind of corrections. Let's see, what time is it? It's, I think I break here, and we continue with this next topic after the break. So let's take 10. That would mean we meet again 10 past, more or less. So 10 past is after the break, and see you then.